So thanks everyone for sticking around. I'm Luke Finnerty. I just started a postdoc at the University of Michigan, but today I'm going to be talking about some extensions of my thesis work, which focused on high-resolution spectroscopy of hot Jupiters. So we've seen this plot a couple times over the past 2 days. These are known exoplanets. Mass on the y-axis, semi-major axis, or period, or semi-major axis on the x-axis. The planets we found are mostly pretty different from the ones in our own solar system. And so if we want to understand kind of a global picture of planet formation, we need to be understanding exoplanets. And today specifically, I want to focus on the hot Jupiters because we're about a month away from the 30th anniversary of the first discovered hot Jupiter. And we still don't really know how they formed. This has led, especially in the last 15 years, to this search for chemical tracers of formation. The idea is maybe we can look at the composition of a hot Jupiter atmosphere today, map that back to some location in a protoplanetary disk, and say how it formed and then how it got where it is today. The problem with that is that disks are really complicated, and there's all sorts of different effects that compete with each other. And so this has been motivating this broader chemical inventory where we're now not just looking for carbon and oxygen, we're also looking for things like isotopic log ratios, silicon to carbon ratios, to try and get a more global picture of these atmospheres. One of the ways we can do this is with a technique called high-resolution cross-correlation spectroscopy. So the idea here is you treat a hot Jupiter system as a spectroscopic binary. Over a couple of hours, lines associated with the star or the Earth's atmosphere don't change much. So that's these fixed features in your high-resolution spectroscopic time series. But any spectral features associated with the planet, they'll be much weaker than the star, but they'll have this really rapid time-varying Doppler shift. And so we can essentially divide out anything that doesn't change in time, and that leaves us with this time-varying signal associated with the planetary atmosphere. So what this looks like in practice is something on the right here where we've taken a time series of 70 frames from K-pic and the K-band. And for each frame, we cross-correlate with a model of what we think the planet atmosphere might look like. And so the color is essentially the cross-correlation value divided by some noise. We started when this planet was during secondary eclipse, so blocked by its host star. We didn't expect to see anything, and indeed we don't. But then as soon as the planet comes out of eclipse, we see this day-side emission signature that roughly tracks the expected ephemeris. We can then vary the RV semi-amplitude and the systemic velocity that we use to sum over this time series, and that's how we make these KPV sys diagrams here that you've hopefully maybe seen if you were, I think, in the KPF session yesterday too. We can also vary the template that we use to do this cross-correlation. And we can iterate and do a retrieval to find the best pressure temperature profile and the atmospheric composition of the planet. And in particular, we're sensitive to the ratio of different spectral features. And in the K-band, that's mostly water and CO. So we had some initial successes with this in kind of 2022 when we built that out into a large survey that ran over the lifetime of K-pic. This was a huge investment of telescope time, which I'm very grateful for. And it's let us span kind of the whole hot Jupiter population. But today what I want to talk about specifically is what we're doing in this last semester, which is an L-band follow-up for 10 additional targets. So why do the L-band? One is that it's just unique. There's not that many instruments that can access this portion of the spectrum. But it's also really good for probing cooler planets. So the y-axis here is the flux of the planet relative to the flux of a host star, assuming they're black bodies. The x-axis is wavelength, and then I've shaded in, this is the K-band, and then this is the L-band here. This black line is roughly where we're confident that we can make K-band detections. As you get lower, things get more and more tentative. But what you can see is that there's a number of planets that are in this kind of too cool tentative regime. They actually do get to contrasts that we can reliably detect out in the L-band. And even planets that we can detect in the K-band, their flux relative to the host star is better in the L-band. Now, the reason it's not quite that simple is the thermal background. So this is a raw frame in the L-band off of NIRSpec. You can see the spectral orders are these vertical lines. And you can see immediately that the background is hugely variable. There's about 100 counts of background at 3 microns, and there's about 12,000 counts of background at 4 microns, and that's in 60 seconds. We're background limited in terms of signal and noise. We're kind of just buried in the background, and it's actually setting our integration times to avoid the nonlinearity just off the thermal background. Now that's potentially worth it because we get access to a bunch of really interesting molecules. So this is opacities in the L band, and the shaded portions are the actual parts of the spectrum you can get on the near spec detector. And what you can see is there's these really strong methane features, which are particularly interesting for cooler planets, because we expect the dominant reservoir of carbon to shift from carbon monoxide at high temperatures to methane at lower temperatures. There's also water, hydrogen sulfide, and ammonia throughout. So if you're interested in probing non-equilibrium chemistry, this is a good bandpass to be looking in. And there's even maybe at the very red end, the silicon oxide bands that could give us some information on the refractories if we can get it out of that crazy thermal background that we're having to deal with. So that's right. We started with a kind of one of the classic test cases, which is HG209458b. This is sort of a benchmark hot Jupiter. We made independent detections in both the K and L band, which is great. So this is working. We can deal even with the higher background levels and lower spectral resolution in L. And then when we combine those, we get a nice little boost in the detection strength. And what was exciting is when we went to go do our atmospheric retrievals, we actually got results that were in very good agreement with JWST. We detected water and no other molecules, and previous ground-based high-res studies had claimed the presence of a bunch of these other molecules, methane and ammonia, hydrogen sulfide, all simultaneously together. Didn't really understand how that kind of atmospheric chemistry was possible. So it's nice to resolve that tension then with those JWST observations and get a more plausible atmosphere. These limits are also only about 1 dex worse than the limits from JWST, and this is with 1 night total of ground-based observing time rather than using a space telescope. So that's great, but it's an easy test case. So the next target we looked at was HD102195b. This is now a target. It's an equilibrium temperature about 1,000 Kelvin, so it's in that transition from carbon monoxide dominated to methane dominated. And there had previously been claimed water and methane detections for this target, so we were hoping we could verify that. Now, in this case, we don't actually make a detection in the L band data on its own. We do make a kind of weak detection in the K band. Things maybe get a little better if you combine K and L. But when we go to the retrievals, actually, the L band data is really helpful in getting us this constrained methane abundance. So we measure abundances of water and methane. We confirm that previous methane detection from back in 2019. And specifically, we get a pretty good constraint on the ratio of water to methane, which is telling us something about the C to O ratio of this planet. So that's great. Can we go even higher contrast? So we tried Gliese 436b. This is a warm Neptune around an M dwarf, 660 Kelvin. We maybe make detections in both of the K-pic science fibers we used, and then if you combine them, you still see it. We think this offset is related to our data processing. We can reproduce it in injection recovery tests. But it's a bit odd because our retrievals are preferring a thermally inverted pressure temperature profile, which is in tension with JWST that preferred a flat spectrum. We also have a continuum mismatch, which is, again, maybe related to the high-res data processing. So we're trying to understand what's going on here, whether this is like a weak inversion that's forming above clouds, or whether this is a false positive. And actually, the last night of K-pic observations is scheduled for December 29th, and we're going to try and observe this target again and see if we get something consistent or if we can rule this composition out. And finally, I just want to highlight that this mode is actually quite robust now. So this is HG189733b. We had a previous K-band epoch last week. On September 10th, we observed an L-band, and we already have a weak detection. I was hoping the retrievals would be done, but I actually only just got the email that the cluster finished. So this is just based on the test model I had, but we get this nice boost when we combine the K and L band data. And we can do this with the data reduction pipeline that we have already without having to do kind of bespoke background subtraction. So I think I am just about at the time limit. I do just want to say L-band is great. Longer wavelengths are great. And we shouldn't cut things off at 2.5 microns because that's where the thermal background starts to get funky. You can deal with the background.